Welcome! We're about to dive into a topic that sounds like it's straight out of science fiction, but it's quickly becoming a reality: quantum computation. Now, you might be thinking this is just about making computers faster, right? Well, it's so much more than that. We're talking about a completely new way to process information and maybe even understand the universe itself. To really get it, we've got to start with the absolute basics, the building blocks. So, to understand this quantum leap, we have to look at how our current computers work. Everything you're doing right now runs on bits. A bit is just a simple switch, It's either on or off, a 0 or a 1. That's it. But a quantum bit, what we call a qubit, completely shatters that rule. Thanks to the wild, weird world of quantum mechanics, a qubit can be a 0, a 1, or, and this is the crazy part, both at the exact same time. And that right there, that bizarre ability to exist in multiple states at once, that's the secret sauce. It's the key that unlocks an entirely new universe of computational power. So let's dig in a little deeper and see how that's even possible. This mind-bending property is called superposition. And probably the best way to wrap your head around it is to picture a spinning coin. While it's spinning in the air, is it heads or tails? Well, in a way, it's both, right? It's only when it lands, when you measure it, that it has to pick a side. A qubit in superposition is just like that spinning coin, holding the possibilities of 0 times 1 all at once. And that's what lets a quantum computer check out millions of possibilities simultaneously. But here's the thing, superposition is just one piece of the puzzle. It's the first tool in a whole new toolkit. There are 3 core quantum principles that, when you put them all together, give quantum computers their absolutely incredible power. The second tool is called entanglement. This is the one that even made Einstein scratch his head. Imagine you have 2 of those spinning coins, but they're, magically linked. The instant one of them lands on heads, you know, without even looking, that the other one, no matter how far away it is, has landed on tails. Entangled qubits have that exact same spooky connection. Their fates are intertwined, and that allows for these powerful correlations that classical computers can't even dream of. And the third tool in our kit is interference. You can think of it like a pair of noise-canceling headphones. So you've got all these qubits in superposition, and they're creating this storm of possibilities, right? A ton of noise. Interference is the magic that cancels out all the wrong answers, just like headphones cancel out background noise, so that the one correct answer comes through loud and clear. It's how the computer finds the signal in all that quantum noise. So, okay, we've got this amazing toolkit: superposition, entanglement, and interference. Cool. But what can you actually do with it? Well, it allows us to start tackling problems that are practically impossible for even the biggest supercomputers on Earth to solve today. Let's take Shor's algorithm as a prime example. If you ask a classical computer to find the 2 prime numbers that multiply together to make some massive 100-digit number, well, it might take that computer thousands of years to figure it out. But a quantum computer running Shor's algorithm, in theory, it could crack it in just a few minutes. And this perfectly shows just how disruptive this technology is. Why? Because the fact that it's so hard to factor huge numbers is the foundation of almost all modern encryption. We're talking about the stuff that protects your bank accounts, your emails, all your online data. Shor's algorithm is both this huge threat to our current security, and at the same time, it's the key to creating a whole new generation of unhackable communication. All right, next up we have another total game changer: Grover's algorithm. Think of this one as the ultimate search engine. Imagine you're in a gigantic library with millions of books, but they're not organized at all. It's a total mess. Finding one specific sentence would be a complete nightmare. Grover's algorithm gives you a major speed up for exactly that kind of messy, unstructured search problem. The potential impact here is just massive. This could completely change logistics by finding the absolute best routes for a global shipping company. It could give a huge boost to AI by helping it sift through enormous datasets to find patterns way more efficiently. It's all about finding that needle in a cosmic haystack and finding it much, much faster. Now, after hearing all of this, you're probably wondering, okay, if this is so great, why don't we have these incredible machines everywhere? And that brings us to the great challenge: actually building them. You see, the same quantum weirdness that makes them so powerful also makes them unbelievably difficult to engineer. Right now, scientists are trying out all sorts of things to build stable qubits. Some are using these tiny superconducting circuits that have to be cooled to temperatures colder than deep space. Others are using lasers to trap individual ions, or even manipulating single particles of light called photons.
Each approach has its own set of pros and cons, and honestly, it's a race to see which one can scale up the most effectively.
But the biggest enemy for every single one of these approaches is something called noise. Qubits are just incredibly delicate. The slightest vibration, a tiny magnetic field, a small change in temperature, any of it can mess up their quantum state and just destroy the information they're holding. This process is called decoherence, and it creates a ton of errors. So a huge part of building a working quantum computer is figuring out clever ways to perform error correction to keep the computation safe. So where are we right now? Well, we're in what experts are calling the NISQ era. That stands for Noisy Intermediate Scale Quantum. Noisy because, like we just said, our qubits are still super prone to errors. And intermediate scale because we can't build the millions of stable qubits we'd need for those world-changing algorithms. Not yet, anyway. These early machines are powerful, for sure, but they're not the perfect, flawless computers we're aiming for. But even in this NISQ era, we are absolutely standing at the dawn of a new age. As researchers chip away at these huge challenges, the real-world impact this whole paradigm shift could have on science, on medicine, on our entire society, it's truly breathtaking to think about. So what does that future actually look like? Well, it means designing new life-saving drugs because we can finally simulate molecules with perfect accuracy. It means creating brand new materials for things like ultra-efficient batteries. It means optimizing global financial markets, building smarter AI, and creating climate models that could actually help us tackle some of our planet's biggest problems. And in the end, it really all comes back to this one powerful idea, which this quote just nails perfectly. The real revolution here isn't just about speed. It's about being handed a completely new language to speak to the universe with, letting us ask questions and find answers that were simply out of our reach before. So I'll leave you with this last thought. For pretty much all of human history, we've been solving problems with one type of logic, classical logic. Now we have a completely new one. So what problems that we think are impossible today will become solvable tomorrow? What are we going to discover when we can truly compute with the fundamental rules of reality itself? The possibilities? Well, they're just starting to unfold.